In this video, we'll just talk briefly about disproving the existence of limits for two-variable or multivariate functions. And so one of the problems that we often get is that it's hard to prove limit existence. But let's write out just a couple of characteristics. A limit, the value of the output, L, exists if this is really implying when x and y are approaching a certain ordered pair, that the z value that we get is constant. It's the same value when approached from every direction. The challenge, though, is there are too many directions from which to approach. So if we think about, if I quick sketch an xy plane here, and we sort of imagine that from this center we have a z-axis coming right out at us, and let's say we're approaching the point 0, 0. So we could approach this from many different directions, and even from curves of all sorts, or even wiggly functions from all kinds. And the problem is that, or even the axes. So we need to be able to approach these from any direction and get the same value. Well, how do you do that? How do you check it from every single direction? In the Calculus 1 course, we learned to approach it from two directions because there's only one variable and you either approach it from the left or from the right. So how do we disprove the existence of a limit then? Well, at least we'll learn how to do something with it. So we can actually approach the desired ordered pair from at least just a couple of different directions and show that the z value, that the L I get from one side is a different L from the other side. So therefore, the z value is different coming from different directions. So let's take a look at such an example. Now we can do this again along a curve, a line, etc. So let's consider this ugly looking function, f of xy equals x squared y over x to the fourth plus y squared. This does not have a limit at 0, 0. By examining the limits of f as x approaches y, as xy approaches 0, 0 along the line y equals x and along the parabola y equals x squared. So here we're told that we're going to approach 0, 0 along these two functions. Well, what does that mean? That means that, again, if I kind of imagine that this is the z-axis coming out at us, that if I approach the point 0, 0 along the line y equals x, which we know is just the line with slope 1, so I'm going to approach it along this line from this direction, I'm going to get a z value. I'm going to do the same thing, and I'm going to approach it with the parabola y equals x squared. Well, y equals x squared would be, 1/2 of y equals x squared would be just this portion of the parabola, and then again, this is just this straight line y equals x, and this is just part of the parabola y equals x squared. And it doesn't matter whether, I approach it from this side. The point is, if I approach it from along one line or one function and along another, and I get a different value of z, then I know the limit doesn't exist. Okay, so what I'm looking for is the limit as x and y approach the point 0, 0 of x squared y over x to the fourth plus y squared. Okay, well, how am I going to do this? So I want the y value to always be, we'll start with a linear function. I want the y value to always be equal to x. Well, cool. That actually allows me to make a substitution then. If y is always equal to x, then this is the same as the limit as x and y approach 0, 0. What happened there? Or y equals x. And, well, okay, so that means I can replace the y variable with x. So I get x squared times x, and x to the fourth plus, well, y squared is really, or y is equal to x, so if I replace y with x here, I get x squared. Okay, now again, the only reason we can do this, it's hard to know what curves or functions to approach 0, 0 with, but we're told here which ones we should use and show that we get different limits. Well, now this function is all in terms of x. So there's no sense in me having to let x and y both approach 0 because I've eliminated y strategically, algebraically, by way of saying that I'm going to do it along the line y equals x. That allowed me to assume that the y and the x were always the same. Therefore, I could make the substitution and replace y with x. Okay, so this is going to boil down to the limit of a single variable x approaching 0 of x cubed over x to the fourth plus x squared. All right, well, let's think about this. As x approaches 0, what is going to happen to this function? Well, I see one thing that I can do is there's a common factor of x squared in both the numerator and denominator. So I'm going to do a little bit of algebra here because I can't plug in 0 yet. So remember, the idea of limits is that you want to perform some algebra to get it down to a form where you can simply plug in the limit whenever possible. And that's what these problems are all about. So x squared, if that gets factored out, x squared plus 1. And now I can cancel those out. And now this becomes the limit as x approaches 0 of x over x squared plus 1. And now notice that by doing that cancellation, I can plug in 0 for x and evaluate this. I get 0 over 0 squared plus 1, which equals 0. So that means the limit of the z value that I would get if I traced along y equals x. Now, again, this is I'd be basically writing along an elevation, but my elevation would be approaching 0 as I approach the origin from that direction. I'm going to do the same thing, but now I'm going to approach it along the parabola, and the goal is I'm going to disprove that this limit exists by showing that if a friend ended up coming to this coordinate by following this type of path, that they would come to a different point than I would. Very much the same process, which is kind of cool. The limit as x and y approach 0, but now where y is going to equal x squared. Okay, so I'm only going to approach it from points where y is equal to x squared. Okay, well, that's going to mean that if y equals x squared, I'm going to get x squared times x squared, because my original function has a y there, and then over x to the 4th plus I'm going to replace y with x squared, so I'll have x squared squared, which is x to the 4th. And, oh, cool, so now I notice that in the numerator I'm going to have again the limit. Now I only need to worry about as x approaches 0, because again, there's no y in here, so y approaching 0 is not going to affect the evaluation of this limit. So I have x to the 4th, and in the denominator I have x to the 4th plus 1 copy of x to the 4th, which is 2 copies of x to the 4th. And now I can cancel that out. So what I'm left with is the limit as x approaches 0 of 1/2. Well, in this fraction, 1/2, x has no implication whatsoever. So regardless of what x is, this ratio will always be 1/2. And now notice that these two are different, and thereby, if I get a different limit coming from two different directions, then the limit does not exist. Simple as that. And that's kind of much easier to disprove something because I only have to approach the x and y pair from one direction and realize that I get different values. So that's kind of the idea here. If we could approach it try to approach the function along the x-axis, well, what would that allow me to do? If I approached 0, 0 along the x-axis, well, that would mean my y component is always 0. And same thing I could do here. I could approach it along, say, the positive y-axis, in which case my x value would always be 0. So hopefully this helps to kind of orient things. This is kind of the approach that we'll limit ourselves to, but there are other strategies. There's this idea of the squeeze theorem and stuff. Lots of different algebraic techniques that we could use, all pretty cool. So we'll stop there.